Hello and welcome to the second video of the Heroes MOOC. This second video is going to be dedicated to primary resources for green and digital transitions. The video is brought to you by Michel Cathelineau, Yana Zavarnik and Olga Chernoburova. Let's start with a brief introduction. What are critical and strategic raw materials? Critical raw materials are characterized with two main parameters: economic importance and supply risk. If a material is crucial for a strategically important sector, such as, for example, defense, and its supply is limited to only a few countries outside of European Union, and in addition to that, substituting is complicated, then this material has high chances to meet the conditions to be considered critical. European Commission publishes critical raw materials lists from 2011, approximately once every 3 years. It was 14 critical raw materials in 2011, 20 in 2014, 27 in 2017, 30 in 2020, and it was 34 in 2023. Notion of strategic materials was introduced in 2023. These materials bear strategic importance. They can, but don't necessarily have to, meet the criticality thresholds. An important initiative, European Critical Raw Materials Act, addresses the need to diversify and secure raw materials supply in Europe. On the screen we can see the results of 2023 European Union Criticality Assessment. European Commission established and over the years refined the methodology that allows to quantify the economic importance and the supply risk of materials. If a material is characterized with a supply risk of 1 and above, and economic importance of 2.8 and above, it is considered critical. Strategic materials are highlighted in green in the slide. We can see that copper and nickel are considered strategic, even if their supply risk is relatively low if we look at the other materials in comparison. Critical Raw Materials Act aims to meet EU's demand for strategic raw materials at 10% for extraction, 40% for processing, and 25% for recycling by 2030. In this framework, in March 2025, European Commission selected 47 strategic projects for European Union aiming to develop raw materials sector and diversify the raw materials supply. Over half of these projects comprise extraction and or processing, around 20% of projects recycling activities, and lastly 2 projects are dedicated to substitution.
Metals are absolutely essential for energy and digital transitions. But frequently, newspapers and media announce regularly the end of resources on Earth. It is not new. Club de Rome has announced the end of most resources in 1975. Some studies like this one from Cairo also shows that we are going to the exhaustion of reserves, and frequently newspaper announce shortages. To this shortage announcement, we have to also to look at the lessons from geologists, and especially what they think about the reserves and resources. How does the exploitation change with time? We had considerable changes with time of grades, cut-off grades, and especially the technologies. So, could we satisfy our future needs? To begin with these subjects, we will look at the definitions of the primary resource and reserves. What is the difference between a proven reserve and a resource? The proven reserves are metal masses in blocks, in geological blocks, where the amount of data is sufficient to perfectly define the mass of metal. The resources, in general, are proven or probable possible reserves in a country or a deposit. So it's totally different. The cutoff grade is the lower grade limit of the economically viable ore. That means that where it is profitable to exploit. Reserves and resources correspond to a relatively abnormal concentration in the Earth's crust. Generally, we exploit the reserves, that means at the maximal ore grades. But in fact, there is on Earth a lot of rocks which contain lower grades or even the normal, between comma, grade of the metal in a barren rock. All these rocks, in fact, can be exploited if it is economically viable. So the theory of Skinner was that the lowest grade and the barren rocks could not be exploited because of technological problems. But this has changed with time. And considering the red part in this diagram, in fact, it is constituted of different parts of the ores, those which have been already exploited in blue, and the orange part, which is a reserve. Reserves, some of them are above the cutoff grade, and they are typically exploitable now. The other part in orange could be exploited in the future if the price of the metal increases. About the reserves in a deposit, we have to have in mind that the metal distribution is quite heterogeneous. In the past, in nickel deposits, like those in New Caledonia, you see here at the bottom, you see the ores which were exploited by hand. They were around 10 to 15% rich in nickel. But now we are exploiting ores where it's impossible to see clearly the nickel. It's a brown rock with around 2 to 2.5% nickel. And in the above part, in the oxidized part, the grade is around 1 to 1.5% nickel. So the challenge here is to define the distribution of the nickel content in the rocks. Here you have a nickel ore from New Caledonia. 1 century ago, the garnierite, that means this talc, nickel-rich talc in green, was exploited with a hammer. But now the ore is this brown part here, you see here, which is composed of the same talc mixed with iron hydroxide. And the ore grade here is around 2 to 3%. But of course, in the garnierite, the ore grade was much higher, around 10 to 20%. But now, with the exploitation and the improvement of technology, it's possible to produce high tonnage of nickel from this brown part in the saprolite. So a summary of our reserves are estimated about the cutoff grade. First of all, we have to define the cutoff grade. We have to generate a 3D block with all the data from the drillings and to extrapolate in the volume the different distribution of grades, to estimate the reserve in terms of mass of metal, and to clarify the type of reserves. That could be below or just around the cutoff grade or above. When we look at the history of the mine activity, there are strong evolutions, especially a decrease, a spectacular decrease in the ore grades. So the decrease in the ore grades is a very warning factor. There are others, especially the fact that for some deposits there is no discovery since 10 years or 15 years. It's the case of copper in particular. And the third warning factor is the fact that we have a deepening of the mine, but the deepening cannot reach more than 2 kilometers. A good example of this decrease in the ore grades is provided by the Bingham copper deposit in USA. This deposit is characterized by a huge amount of displaced mass of rocks, just because the grades has decreased by a factor of 10. But the production remains nearly the same with time, And we can conclude here that for the moment, technology has solved most of the problems of metal production. If we continue on the example of copper, copper is announced with shortages frequently, but in fact, if we look at the 2 past decades, the reserves have been multiplied by a factor of 3, but the demand was only multiplied by 2. So in this particular example, during 2 or 3 decades, the technology has solved most of the problems. To perfectly define the ore grade, it's necessary to take into account the densities of the different metal bearers in a rock. That means a rock is composed of different minerals. So the density, the bulk density, is the mass of the rock divided by the volume of this rock. But we have to take into account that the ores are complex assemblages. In the particular example of a porphyry copper deposit, you have small veinlets of chalcopyrite, and which are cross-cutting the granites. To calculate the density of the ore, we have to take into account the density of the rock, which is composed of 2 or 3 minerals, quartz and 2 feldspars, and the density of the veins, which is composed of quartz and chalcopyrite. Chalcopyrite is the heaviest mineral, as it contains iron and copper. By combining all these data, we can reach the information about the density of the ore, and we can calculate as a ratio the ore grade. That means the amount of copper present in the rock. So here you have chalcopyrite, pure chalcopyrite, which is a sulfide of copper and iron. The chalcopyrite contains 34% of copper. Here it is pure, but in a deposit, of course, it occurs as veins. Here you have a Bingham deposit vein, where you see the chalcopyrite and quartz veinlets, which are cross-cutting the granites. Here the grade is much less than in chalcopyrite, because you are diluting chalcopyrite with quartz, but also the 3 minerals composing the rocks, that means quartz and 2 feldspars. Here you are around 10%, 8%, because you have big amounts of chalcopyrite in the vein. You have to imagine that with time the grade has decreased, and now the grade is around a fraction of percent. That means much less chalcopyrite grain in the rock. But it is still feasible to extract the same amount of copper from this deposit due to technological improvements. At the scale of the deposit, of course, we have to take into account the measurements which can be done at the sample scale, but then we have to extrapolate to the drill core scale and then to the deposit scale. So it's a series of complex calculations to estimate the ore grade, the bulk ore grade in a deposit. Density is a crucial parameter, but we need to regularly update this data because the ore could change with time in a deposit because we are not exploiting the same part with time. So we have seen that the cutoff grade is mostly an economic parameter. So we need to have in mind some economic considerations. Most economists know very well this process of price fluctuation. It depends on the availability, in our case of a metal, and from the demand. If the demand is excessive, the price rises, but if the price rises, then the demand will decrease. So there is a kind of equilibrium, and this is a complex system. The equilibrium between supply and demand is essential to understand the fluctuations of prices. Of course, the production could be affected by the renewing of the reserves. For instance, the demand could be affected by some instantaneous clearance. For instance, now we have a decrease in the price of lithium and nickel just because Chinese producers are not selling so much cars and the stocks are just cleared. So in that case, the price decreases, but the price could increase in the case of import taxes. This is typically what is happening now. So the export restrictions and also some technical difficulties of extraction, but mostly of metallurgy, could affect the instantaneous availability of the metal, and then we have an increase in the prices. The metal price is a complex combination of different factors. It depends on the cost of mining, grinding, mineral separation. Of course, it's a technology. The availability depends mostly of hydrometallurgy or smelting and the cost of these technologies, and also from SEG regulations, especially in environment and also human and social rights. It is particularly difficult to predict the evolution of metal prices with time. And this is one of the main failure of the economic prediction, is that most of the predictions are false. So after this short survey of the factors controlling the availability of metals for our needs for the energy transition and digital transition, we have to say that generally geologists are working well and also metallurgists. So the problem is not technical, is not linked also to reserves or resources available in the world. It is mostly an economic problem. So these economic problems are mostly linked to geopolitics. We have strong examples now with the commercial wars. But also people can play a role, especially on sobriety and recycling. So this is what we can encourage.
And in this table, you will find the main takeaway message from the presentation that you have just seen.